Okay, so welcome everyone. I'm Professor Clark Nguyen. Welcome to ee105. This is Microelectronic Devices and Circuits. Just to make sure you can all hear me, can someone just say you can hear me or thumbs up? Excellent, good. All right, so this is our first lecture and a lot of logistics that we'll cover today. I'll talk about the course syllabus, we'll talk about the schedule for the course and how we're going to do the labs. As you know already, this course is going to be fully virtual this semester, I believe, because I don't think we're coming back over the semester given what's happening with the pandemic. But just to let you know, you saw what happened. Those of you who were here when it happened, I started a recording. You saw the countdown in the beginning of this. These lectures are being recorded. They're not being recorded via Zoom, though. They're being recorded by way of Camtasia because Camtasia just works better. That means you're not going to get a recording of me. I guess you could see me in a window right here, but for most of the lectures, you probably won't be able to see me anymore because once I start writing on my tablet, I'm going to have to orient my tablet in a way that you can't see me, so I'll just turn the video off. But if you need to see me, I'm not sure why, but you can see me in office hours. I will definitely show myself in office hours, which will also be virtual, which we'll also talk about as well. Okay, so I already mentioned all lectures are going to be recorded, and as they're recorded, they will be posted on the website for the course. And so from Piazza, you all know that the course website is not going to be B-Courses. It's going to be the custom website that we have for the course. And the reason for that is because I like these courses and lectures and everything to be public to the world. There's a lot of people out there who, if they can stick with it, can actually learn this material without getting a degree or a grade or something like that. And I think it's great if people can do that. And that does happen across the world. We do get questions from people across the world about homeworks and different things in the class. So that's why our website is going to be completely public. And those videos will be basically YouTube videos that are not public, but that you can link to from the website when you go to the lecture page of the website. More on that later. For all the lectures that I do, so everything that you see in front of me, everything that I write, I'm going to create PDFs of that and post it also to the website. And so that's going to be on the big lecture table there. The PDFs after the lectures will be available nearly immediately. The videos might be a couple days later because from Camtasia I have to do post-processing to create MP4s and that. If you miss a lecture, you can always watch the video. If you cannot attend these lectures at this time because you're international or not in the US, you can also just watch the videos. A warning though to those who would rather just watch videos and not come to the live lecture. Of course, if you come to the live lecture, you can actually ask questions and you can hear, you can sort of influence what happens during the lecture. But the other thing is if you think you're going to watch the videos after, often you don't have time to do that because you're with a pretty busy schedule, right? Especially during the end of the semester, you have projects and different things that'll be due. Try your best to come to the live lectures. It's better for you, and it's better to be able to keep up that way as well. This week there's almost nothing happening except this administration, and then I'll have some sort of background material that I think I'll give you on Friday, but it could be new to a lot of people too, depending on what your background is. Your first homework is going to come next lecture. So on Friday we're going to release that homework, and as I'll say a little later, the homeworks will be due the next Friday. And we'll have about one homework per week as we go through the class. The discussions start next week, so there's no discussion today. And the labs start the week after next. So even next week there won't be any labs, but we will put on the website your first lab for lab section that will be on Monday, September 9th. And as I'll say later on, you're going to need to do the pre-lab before you get to that section. And whether you can actually do the physical lab is going to be a question. Because we'll talk about how we try to give you access to a physical lab. You all sort of know that we're going to send out lab kits, but how that works we shall see. We're all sort of making this as we go along, making things up as we go along this semester. In terms of getting into the class, on the last check the class was full, but it keeps vacillating. So it goes from full to 2 slots available to full to back and forth. And we expect that to happen over the first couple of weeks. That's why we're not sending you the lab kits just yet. We want to make sure that everything settles down. That's also why we're not sending out that information sheet where we'll collect your address and ask you a few questions, get your guarantee that you'll send the lab kit back to us, for example. We're going to send that this Friday, collect your information, and we probably won't send lab kits out till next week sometime, probably end of next week. So if you do the math, that means you're not going to receive that lab kit till at least a week after, maybe 10 days after, depending on where you are. And that means that the physical labs will not start until at least a few weeks from now. And so that's by design. So your first lab, you're actually not going to do the physical lab. You're just going to do the pre-lab, which is all written material. It's theory and writing to prepare for the physical lab. And then the physical labs will start hopefully when you receive your lab kit, provided you can get your lab kit. So I will say right off the bat that there's some issues right now with sending out lab kits, and that the university is sort of balking a bit at sending lab kits internationally. These have to do with government regulations. You know that our government right now is having issues with some others and that sort. I think that those will be fixed in a couple weeks, so I think in the end everyone will be able to get a lab kit. If not, we'll have to think of something, and we will. So it's not to worry. I'm just telling you what may or may not happen in the coming weeks. So today, what are we going to talk about? So I'm going to say a few things about myself first, because I think it's important that you know who's lecturing to you, where I'm coming from. Then we'll go through the course syllabus, so all about the course and how things will run. We'll look at the course schedule, so the lecture topics per week. I'll talk a little bit about the grading information and policy, and if we are able to get to this, we'll start reviewing signal types, which are things that I think you should know of, but some of you come from very different backgrounds in this class. And so, if we can get to this, we'll start talking about digital communications, but that's probably going to be more for the next lecture. I think before I start into things, well, no, why don't I start in and just say a few things about myself first, so you know who's lecturing to you. And so here it is. So about me. So I got my PhD from this school, from the University of California at Berkeley in 1994. After 1994, I left Berkeley to teach at the University of Michigan. So I was faculty at there for about 10 years. And in 2006, I came back to UC Berkeley. My research is on microelectromechanical systems. So this is actually tiny mechanical devices that physically move on a wafer. So you can integrate them, some of them with transistors, and they can do things like create sensors, like your automobile, for example. When your automobile crashes, I hope it doesn't, the sensor that deploys your airbag is a MEMS sensor. Even in your phones, if you rotate your phone from landscape to portrait, there's a MEMS accelerometer in there and maybe a gyroscope that will detect that you've rotated that, and that's how it knows it's rotated, and it can then change your screen from landscape to portrait. If you drop your cell phone, many don't know this, but as soon as you drop your cell phone, it detects that acceleration change. It knows you've dropped it, and it prepares some of the things in your cell phone for impact. And that actually saves some of the electronics in your cell phone. And so that's sort of what MEMS technology is about there. We're not going to talk a lot about MEMS technology in this class. We're going to talk about the technology that goes together with it, which is transistor level circuit design, to detect how these mechanical things move and basically give the output for sensing. But that's my research. No need to really worry about that. As far as teaching, at the University of Michigan, I taught mainly transistor circuit design courses. I won't mention any names of courses there since you won't know, but at UC Berkeley, the courses I've taught is 105 a few times. 140 I taught for the longest time, about a 10-year run at 140. Then I stopped to make room for, say, some of the newer faculty who want to teach 140. I haven't taught 140 in 5 years now. 143 is a class on fabrication, so semiconductor fabrication. 240A is sort of the graduate portion of 140, and then W240A is an online course that I taught that is associated with 140. It's a lot of 140 type material here. 243 is the graduate version of the fabrication course, and then 245, 247B, W247B are all about MEMS. And so that's my teaching background, what I've been teaching. In 2001, so this is my I guess, industry background. I founded a company called Desera. This was the first company to commercialize vibrating RF MEMS technology, and you all have these now. They're all in your cell phones. They're all in your Apple Watches and that sort of thing. These things, they tell time for you. And so it's a very high volume product. It's pretty cool to be able to do that. That doesn't mean I'm filthy rich. It basically means, you know, it depends on your margins, right? You can sell a lot of stuff if your margins aren't high, then you're not necessarily filthy rich. But the cool thing about this is there's a product based on MEMS technology out there that pretty much everyone has right now. Beyond university and I guess entrepreneurial experience, from mid-2002 to 2005, I spent some time in Washington, D.C. At DARPA. This is the Defense Advanced Research Projects Agency. This is a funding agency, and so I basically gave funding to a lot of research efforts across the nation. I ran 10 different MEMS-based programs on a variety of topics, so power generation, chip-scale atomic clocks, gas analyzers, nuclear power sources, gyroscopes, on-chip cooling, environmental control, packaging. There's a lot of different things. And so I guess in my experience, and what I'll tell you a couple times during this class is that you might be happiest and you might be able to be most impactful if you try to learn a vast variety of things. So you're studying circuits right now in this class, if you stay in this class, and that's one thing you'll learn, but be open-minded to learn all sorts of different things. The reason why I've had so much fun over these years is because I learned not only electrical engineering, transistors, design, and you know, systems and that sort, but I also learned mechanical engineering, chemical engineering, all these other things that allow me to combine all these different things together to just have all sorts of fun. And this should be your goal in life, basically, to have all sorts of fun. You'll hear more of that from me throughout this semester. But that's some background on me. And so, you know, before we start going through the course syllabus and that sort of thing, let me find a little bit something about you here. And let me ask, how many of you are not electrical engineers? And I don't know if you want to raise your hand to do that. You can raise your blue hand there. I won't look at your names or anything. It doesn't matter. I just want to know. Okay, so we've got, yeah. So usually in this class, we get a good bunch that are not electrical engineers. And that's by design. I think it should be that way. Because what this class does is it sort of teaches you a lot of practical stuff that you ought to know if you're an electrical engineer, but that you ought to know even if you're not an electrical engineer. This is the type of stuff that allows you to, say, fix stuff around the house, if you care to do that. Like when my microwave breaks, I don't go out and buy a new one. I mean, I can, I'm sure everyone can, but I open the thing up and I change things out, and then suddenly it's fixed. And somehow I get some satisfaction with doing that. And so hopefully, you know, after taking this class, you're going to be able to do that too, should you want to do that at some point. A couple more questions for you. How many of you have actually taken 16B? Just go ahead and raise your blue hand if you can on the chat thing. Okay, so that means everyone here. Almost everyone has taken 16B. I guess there's a few who have not, or at least you're not raising your hand. And if you haven't taken 16B, should you be worried? And I guess the answer to that is changing. Because I'm not sure how relevant 16B is anymore to this course. It may be that 16A is the one course that you really need to take, and then there's some other courses in other departments, like some mechanical engineering courses on circuits. The first course on circuits, even bioengineering has that. So we may at some point change the prerequisites for this course to not really include 16B, actually. We're thinking of doing that. So that more people could actually
Something's wrong with your microphone.
Is there?
There was.
It's back to normal now, but
Yeah.
that was scary.
How much did you lose? Did you, was it 5 minutes?
You started mentioning that it was changing the requirement for 16B.
Yeah, okay, so you didn't miss a whole lot. And maybe that's the part that you should miss, actually, because we haven't really decided to do that yet, but we're thinking of that, to make this course only require 16A, but I guess that depends on how much you really learn from 16A and 16B. So that's something that I'll be trying to do throughout the semester, at least in the beginning, to try to gauge what you know, what you don't know. And the reason for this is that the 16s keep changing. And they're changing in a way to remove the material that would be useful for this class. And so I guess I can ask this other question here. How many of you have seen a transistor in previous courses? A lot of people are saying they've seen the transistor. And did you see those transistors in 16B or somewhere else? Let me change that question and just ask. Did you see transistors in 16B?
Yep.
You did? Okay, so some of you took a pretty good 16B then. When did you take 16B? Who saw transistors?
Spring 20.
Oh, as recently as spring 20. Okay, so maybe my information is not completely correct here. I guess the next question would be how much of the transistor have you seen, but we will we'll address that a little later. Okay, so with that, just a few questions for you. Let's move on now to actually talk about the course and the details of the course here, and that's what a lot of this is going to be today. So this is what you can find online on that first page of our website, the home page of our website. It's this sheet here. It's the syllabus, so it sort of gives you all the information you need to be able to function in this class, I suppose. And so first off, there's information on myself. That's my email address. My office hours are going to be Mondays from 3 to 4 and Wednesdays 11:30 to 12:30. All of these are going to be via Zoom, and you're going to get, similar to what you got today, a calendar invite to all of these things before they start. And I guess what's happening, let me just talk about the Zoom for the course right now. The Zoom link that I gave you for the course is for this week, and this week only. And the reason for that is for next week I'm going to give you a new Zoom link, and the week after that maybe even another one, but then after that it'll be permanent. The reason why these Zoom links are changing is because people are adding and dropping the course. And so I want to make sure that when we start getting to steady state in this course, that we've got mainly the people who are enrolled in the course. And that's mainly to avoid any issues with the Zoom bombing and that sort of thing if someone tries to do that. If you have a friend who wants to just sit in on lectures, that's perfectly fine too. Just let me know and I'll send the Zoom link to that person as well. Your teaching assistants are Mr. Kieran Pillow. I don't know if Kieran is here. Is he? He might not be. But Kieran is going to have office hours Mondays 11 a.m. to 12 noon, Thursdays 2:30 to 3:30 p.m. via Zoom. Again, your homeworks are going to be due on Fridays, actually. So there's going to be a lot of Thursday office hours here. Kieran, you're here? There he is.
I'm here.
Okay, so there's Kieran, so you can at least see him there. And then your second TA is Miss Tu-Cuong Jin. I can see her on my screen right now. Tu-Cuong, you might want to wave.
Yes,
Yeah.
I'm here. Yeah.
Yeah.
Nice to meet you.
And so her office hours are going to be Wednesdays 1 to 2 p.m. via Zoom, Thursdays 11 a.m. to 12 noon via Zoom. Hopefully you all can make at least one of these office hours, hopefully more than one. If not, let us know, and we can try to make some adjustments so that we can make sure that you can get to at least one of these office hours for this, if not more than one. You know the lectures Monday, Wednesday, Friday, 2 to 3 p.m. via Zoom. As I'll say in a little bit, I'm actually on kind of an important university committee that meets every once in a while on these Fridays. So I'm going to have to miss some of the Fridays, 2 to 3 p.m., in which case what I'll do is I'll try to find a time that we can all make on those Fridays. And maybe I could try to find that time now. Maybe it's not a good idea to do that now. So if you can't make the new time that I find on Friday for those specific days, it should be fine because I'm recording the lectures again, and you can just watch the recorded lecture. But to make sure that as many people can attend a Friday lecture, let me just kick out some times here and see how your reaction is. So if we do a Friday, and this will just be on those special days, and I'll tell you which special days they are on the schedule. But if we try Friday 11 a.m., how many people could make a Friday 11 a.m. lecture for 1 hour? Show of hands, yeah, blue. Use your blue hand. Ooh, that's not many. Okay, that's a very small number there. It could be that Friday is not possible for a lot of people anyway. Let me try another time on Friday. Let's try something late afternoon. Who can do Friday? I guess my meeting ends at 3, so Friday at 3:30. How many can do Friday at 3:30? In-person lecture. Okay, that's a lot more people, I think. Yeah, maybe that'll be the time that we do it. Maybe then Friday at 3:30, we'll try to do that. And again, those are only special Fridays. Most of the Friday lectures will be 2 to 3. But on those days that I have those committee meetings, we will have to do a 3:30 to 4:30. And those then will also be recorded, so you won't really miss a whole lot if you can't make those. Discussion sections, you know your discussion sections and lab sections. I know you're all signed up to these things, so no need to talk about that. The course website, I think a lot of you have been on that. Office hours, we talked about. And again, we're each going to send you Zoom links for our office hours. And we'll do that before, of course, Monday next week. And probably in the first week, you'll get some Zoom links, and then we'll send another Zoom link on the second week. Same kind of thing, because there's people adding and dropping the class as we go forward here, at least in the first few weeks. And so for course description here, I've written out a certain thing that you can go and read through yourself, but let me do this a little differently. Let me do this using some slides. And so I'm going to pull this up here. And so this is kind of the way that I'm going to be doing lectures. And let me talk about that first. So part of lectures, I'll be using slides like this. And so these are full-blown PowerPoint. There won't be a lot of this, actually, because this is a course that runs best through writing. What you're seeing, what you saw when we opened up, so let me pull this thing down here and go back to this. So you saw these two screens here. They're basically two PowerPoints. And the reason why I do this is because that allows me to put something on the left side and keep that up on the left side while working on the right side. It's like having two blackboards, something that you lose if you just go pure PowerPoint. So for example, later on in the semester, this may be what the screen looks like. You may have a circuit that I'm working on there, and then on the other side, I'm just doing writing to solve parts of the circuit. And so while I'm writing here and drawing things here, I can refer to this circuit, and you can have this on your screen at all times. So that's why I do this double screen sort of thing. It works very well for circuit-like courses, or any course where you need to have some figure up, and you're looking at that figure and analyzing it at the same time. Okay, so that's why you see this mode of operation, but then there's this other mode of operation where I will just go full PowerPoint here. And so that's what we're going to do right now. And so I want to describe this course, I suppose. And so here's sort of, this is not what this course necessarily talks about. It will talk about a lot of this stuff here, but not to the degree where you're really going to be able to understand the full complexity of this right now. What I'm showing here is after you've been through our circuits program at UC Berkeley, this is what you should be able to look at and analyze. And if we taught you correctly, you'd be able to look at this and analyze this in less than a minute. So in less than a minute, this looks pretty complex. But with all the skills that you're about to learn in this class, and you've got to take 140 to really get to this level here, you should be able to just look at this circuit and tell, okay, this is a current source. This is a level shift here. This is an op-amp here. And I can determine exactly what the current is here, exactly what that output voltage is here, exactly what the gain is from one point to another. If you don't know what gain is, you'll learn about that later on. What the impedances are looking here and there in less than a minute. You'd be able to do this if you go all the way through 140. Okay, and so that's a great goal. And I think for a lot of electrical engineers that want to do circuit design, that actually want to be transistor level designers out there in industry, you need to go through 140. It'd be nice if you can get to 142 and 240B, but this is the sequence of courses. So 105, which you're in right now, teaches you the basics of how to get here. It won't tell you how to get all the way here to this kind of complexity, but it'll give you all the basics, what you need to know to start making it in this direction here. This you learn, you can see from 140, and even some of this, the more detailed aspects, the advanced aspects, that's 240B, so that's a graduate course. So what this is saying, it takes you a good amount of time to get to this point right here. Okay, the question is, do you need to get to this point? And I would say for everyone, not necessarily, right? Only if you want to be a circuit designer that's in an analog or digital design house or something like that, do you need to get this far. Not everyone wants to go this far, but at least take 105 to get some practical capability. So what does practical capability mean? That means you want to design something like this. So this is a solid-state guitar amplifier. This is what some musicians use. Not a lot of them because it's solid-state. Solid-state means it's based on transistors. And musicians, interestingly, don't like transistors. And neither do most of you, because when you listen to music, a lot of that music is not amplified by transistors. It's actually amplified by vacuum tubes, of all things. Most of it is. But if you had a solid-state guitar amplifier, maybe this is a Fender Princeton Chorus, and if you open up the circuit for this thing, so you open up this chassis and look at the circuit in there, what you're going to see is something like this. And this is something where you already understand a few things. And so here's where I'm going to start writing on this. And so when I write on things, what I'm going to do is stop my video at all times because I'm sort of orienting my computer in a different way here. And so if I look at this, and let me choose a color for this, you can already recognize a few things on this. So if you took the 16s, you know what an op-amp is. And so this thing here, you should be able to recognize very quickly, right? That's a simple op-amp circuit. Okay, you can see in this there's a lot more complex op-amp circuit. So here's an op-amp circuit here that actually is joined together with a transistor. So this whole circuit is using some op-amps, a lot of resistors, some transistors. So that's a JFET resistor, actually, or transistor. It's actually a JFET. We'll talk about, well, we actually won't talk about JFETs in this class, but there's another transistor. That's a bipolar junction transistor. This we're going to learn about in this class. And we'll learn this very deeply because a lot of the circuits out there that you can actually service, they use bipolar transistors. And so a lot of the circuits that you can't service, the more modern circuits like this one in the previous slide right here, you see a bunch of transistors here. This is an MOS transistor. These dominate a lot of the complex IC chips. So your computer, for example, the transistors in there, those are MOS transistors. But those are things you can't service. You can't get into that chip. That's something, if your chip blows up, you just got to buy a new one. Okay, and so that's what a lot of the advanced analog design is right now. But the design that we're going to learn in this class is this type of design, where you don't have billions of these transistors, millions or billions of transistors. You just have a few of them. But you can see them on the board, and you can tell what they're doing, and they're actually doing some very important things. And oftentimes, if you need to fix something, that's the transistor you replace. And if you want to design a new amplifier, you have to understand how to design with discrete transistor design. So in 105, we're going to learn how to build circuits like this, discrete circuits, not as complex as this. This takes some time to get to this kind of complexity too. But this is one of the circuits we'll build. And so this is an amplifier. This is not one of the circuits we'll build. This is the type of stuff that you'll learn to build eventually. Here's another electronic device that you're going to learn how to at least understand how it works, or if you need to fix it. And so this is actually a wireless power switch. This is for lazy people like me who don't want to get off my recliner to shut my TV off or to turn a light on or something. And so what this is, it's got a wireless remote right here. And you hit one of these numbers, it's going to turn one of these. There's 3 of these things around in different plugs in my house. And you know, this wirelessly receives that signal, and it turns on a switch that allows the power to come here from the outlet that this is going into. And so this is also an electronic system, of course, but if you open it up, you'll see this is its board right here that you see on the right, and I can identify a few things. Now on the other side of the board is the actual relay switch, and it's got thermal fuses and different things there, but on this side, you can see right here, that's a bipolar junction transistor. And you can see in this whole circuit, there's just one of these here. So this thing is connected to a bunch, to this thing, and to that thing, and to that thing, and then it makes its way to the switch out there. These are also some smaller transistors, these as well here. But that's a distinct bipolar junction transistor. This is the type of circuit design you're going to learn to do here. You're going to learn what this transistor is doing in this circuit, what other elements to put around it to make it behave the way that it's supposed to get this whole thing to work. Okay, so that's the practical aspect of this class. And okay, I'm now looking up and seeing the chat. Okay, that must have been in the past with my audio. Hopefully my audio is okay right now. Okay, 16B covered very basic transistors. Okay. Okay, used them in labs, didn't really learn them. How necessary is this class for taking ee140? Is absolutely necessary. You should not take 140 without taking this class. What about ee113? Yeah, ee113 is a great class to take too. I just don't have a lot of, I mean, there's not a lot of space to put all those classes there, but 113 is important to do as well. You'll learn about transistors, etc. there. I think I've handled most of those chats there. All right. And you don't like the solder job on this. Yeah, it's a power circuit, so I don't know, it is kind of sloppy too. Yeah, it's a very inexpensive thing, right? So for me, I would fix it just for fun. But most people will just buy it, right? It's $5 or something like that. All right, so this is one thing you'll learn to be able to switch to fix there. And so here now is another amplifier. And this is just, trying to drive the point across that, we're going to look at bipolar junction transistors in this device. We're going to learn MOS transistors in this device, or in this course. Sorry. We'll learn bipolar transistors in this course, MOS transistors in this course. But keep in mind that those are only two of the types of transistors people use. And so this is actually an amplifier here, a Fender Deluxe Reverb for music, that's loved by musicians across the world. So a lot of recorded music on this. And this is not necessarily an old one. Even the modern ones are designed as you're seeing to the right here. It's not using a transistor. It's using a vacuum tube. Yeah, a vacuum tube. I don't know how many of you know because you're all fairly young now, but this is what was controlling your television sets for the longest time. Many, many years ago, decades ago. But even now, it's not even decades ago, this is what's being used to power that amplifier. And so the symbol for this you could see all over the place. There's one tube. There's another tube. This is a dual tube together. There's a lot of tubes being used here. Not a single transistor is being used in this. Why? Because transistors don't sound good to most people. So that, it's a subjective sort of thing, but most people don't like the sound coming out of an amplifier using transistors. These tubes have a certain response, a certain nonlinear response that our ears enjoy quite a bit. That makes the music very nice. And so what you learn in this class will teach you to design something like this. It won't teach you exactly how to do it with tubes. If you want to do it with tubes, you'll have to learn how tubes differ from transistors. We'll do it in transistors, but all of this design that you're seeing here, same techniques that we're learning in this class here. And so this tells you, beyond just the transistor world, learn the basics of this class. And what allows you to design these are the basics. Things like small signal analysis, which I'm not sure you know what it is, but fundamental analysis techniques that we will learn that will allow you to build something like this and do something very practical and make a product or something if you want, based on not something where you have to have thousands, millions of transistors, but on something where you just have a few of them and yet can sell a lot of these and people will enjoy a lot of them. Okay, so that's sort of the message of what this class is about. It's going to teach you that practical stuff, the stuff that you can take apart and fix, you can. Stuff that's simpler, that you can design, you will be able to after this class. And maybe that's the more important thing for you to learn at this stage if you don't want to go all the way out to the 140 level. And there's a bunch of you that don't want to. All right, so let me get out of this. Keep that. Save that. And move that out. And get back to the course syllabus here. What class do we learn to make vacuum tubes? There are no classes that we offer that will teach you how to do vacuum tubes, unfortunately. They're just too old right now. So that's something where you'll have to take what you learned in this class and adapt it to designing with vacuum, circuits using vacuum tubes. All right, so that's my, I sort of covered some of this thing using those slides there. But now let's talk about prerequisites for this course. So currently, they're EE16A and 16B. Looks like 16B at least shows you a transistor. So that's pretty good. Or did you see that in 16A? I won't really ask that completely. So these classes sort of combine those two, but it's pretty light in that. And so this class I know is going to have to go more to the fundamentals than it has in the past. But I'm going to assume you're familiar with the following topics. So one of them is basic network theory. So RLC circuits and analysis methods like Kirchhoff's current law, Kirchhoff's voltage law, that sort of thing, nodal analysis. Step and frequency response, poles and zeros, complex impedance, transient response analysis. So these are things that you've seen to some extent in the 16s or whatever course you have that's equivalent to those. And we're assuming that you know ideal operational amplifier circuit design and analysis. And then we're assumed that you have some exposure to digital logic circuits, so like inverter operation, but I've learned that you don't necessarily, at least in some instances of the 16. So some of you may have never seen a digital logic circuit using a transistor. So that's going to be the perspective that I take in this class in terms of what you know. Basic electromagnetics, fields and waves, potential Gauss's law. The reason for this, you're going to need to know some physics because we're going to talk about physics. We're going to talk about what the structure of the transistors look like. We're going to talk about how they operate, how they're pushing electrons in this direction and what's called holes in another direction, how voltages can go over a threshold and get things to suddenly start working in diodes and transistors. So we'll be talking about some physics. I see that there was a question about, is this related to 130? Yeah, it is. It's related to 130, but 130 is much more advanced. Okay, I don't think poles and zeros were really covered in 16b. That is good information here. Did you cover them anywhere in any of the 16 poles and zeros? Do you know how to do a Bode plot, I guess is a big question there. How many know how to do a Bode plot? Show of hands. Use your blue hands. I'll wait for everyone to chime in. That's not a lot of the class there. All right, so I will teach you how to do Bode plots, but the second question so it begs the question, have you seen transfer functions, polynomial transfer functions? And I guess the answer to that would be yes, because you've solved some circuits before. You have solved some RLC circuits, and those will give you polynomial transfer functions. But how to do Bode plots, how to work with those, okay, I guess I'll take a step back in some of the lectures and make sure that that's covered. I'll be asking you along the way how much you have covered. Okay, someone says, yeah, it's in 16b. Covered in spring 19. Yeah, so that's part of the issue. The 16s have been, they're not necessarily the same every semester there. All right, so moving on here, the text. So what's required? So there's Cedra and Smith is required. So that's microelectronic circuits. You've got some supplementary texts that are not required. So there's also a nice text by Jaeger that's similar to Cedra's. Some people may find it easier to read. It's much more concise. But concise is not necessarily good because that means he doesn't explain as much as Cedra does. That's why I picked Cedra and Smith. Cedra and Smith, they explain everything in a lot of detail. And for this class, you have a textbook, you should read it because it gives you a different perspective. Well, the same material, a lot of the same perspective, but sometimes a different perspective than what I'm giving you. And that's the best way to learn, to get as many perspectives as you can. We'll be using the SPICE circuit simulator in this class, and so there's also this supplementary thing that you can buy, but I guess people have said in recent years this is becoming less and less useful because the SPICEs are changing. And so we'll be using a couple versions of SPICE in this class just to give you familiarity with two types. And maybe this text could be useful for you. Reading assignment. So let's now take a look at the course syllabus here. And so that's this thing. And so this is the tentative syllabus that we're going to be going through. These are all the different topics that we're covering in this class. And so you see the date, you see the lecture number. Out here is readings in Cedra and Smith, that textbook I just talked about. Can you use the old edition for the textbook? Yes, you can, but the older editions will have different homeworks in the ends of the chapters, and so there'll be differences from the 7th edition, but for each homework set that we pass out, we will give you those problems from the book. So you don't even need to have the latest Cedra and Smith. There are going to be some differences, but a lot of the material is going to be similar. So where was I? So your reading sections are here. So try to keep up with the reading because that way you can really understand a lot of the topics that I'm talking about here. These are the due dates for the homework. So you're going to get homework number 1 right here on Friday, and that'll be due the next Friday. And you can see you get homework subsequently after this And, okay, I have to fix this. It's like, you will have a homework assignment here. You just won't have a homework assignment here when you have your midterm. The difference is before I had the class with 2 midterms, now I have it with 1 midterm. And so we'll talk about why I did that in a second. Here's your labs that start occurring. So next week there's no lab. But the week after that, that's lab number 1. You'll see that that'll come online probably Monday next week. And you will not have your physical lab kit by the time of this week. So what we'll do for these labs is you will do just the pre-lab for this. You'll spend a little bit of time with your TA in lab section. And then you will later on actually do the physical lab. So automatically, because of timing and sending kits out and that sort of thing, we will not do all of these physical labs. There's a total of 4 sort of labs that teach you how to use the equipment. Then lab 5 and lab 6 are design projects where you're actually doing a transistor level design there. And so by lab 5 and lab 6, you will be hooking those up physically. But some of these labs here, you'll be hooking up lab 1 physically, but not on this week, maybe this week or something like that. Lab 2 you'll do physically, but it'll be pushed back a week as well. And maybe lab 3 and lab 4 we don't do. It's just a consequence of us being virtual and trying to deal with that here. But getting back to the topics here, so administration today, I'll do signal types there. Then we'll start doing review, and here's where I'll be trying to find out what you know, what your background is, and if you're missing something in your background, I'll try to cover it, or we'll try to cover it in discussion section and that sort of thing. So be as honest as possible of what you know in your background, what you don't know, because the background is important to really move on to understanding the rest of the class. We'll then start moving into ideal op-amps. So this is something that I think you already know from the 16s. But then we'll go into non-ideal op-amps. And non-ideal op-amps means the gain is no longer infinite. The impedances are no longer, the input resistance is no longer infinite. The bandwidth is no longer infinite. We now have finite amounts of those. And that changes a lot of the way that you have to analyze these circuits and their behavior eventually. We'll then go on to talk about generalized elements. And so a lot of this class, when I talk about fundamentals and being able to design either in a bipolar transistor or a MOS transistor or anything like that, the important thing to understand is that they're all nonlinear elements. And what we're doing is this class is really about modeling nonlinear elements, nonlinear circuit elements, and then being able to analyze circuits based on these nonlinear elements. And so that's the skill you'll get. And that then involves some understanding of the devices themselves. So after this, after talking about generalized nonlinear elements, we start talking about devices. And so this is where the physics part comes in, where there's some overlap with 130, but not much. We're doing just it's an overview of it. 130 gets into much more of the physics details. 130 gets into the quantum mechanics and physics that you need to really understand this. We will not touch quantum mechanics as deeply in this class here. But we will teach you what the devices are, how they work. And then after doing that, for both MOS devices, so metal oxide semiconductor FETs and bipolar junction transistors, we'll then start talking about how we actually use these devices, how we analyze circuits of these, and so we'll talk about small signal analysis. That is our crucial analysis technique. That's a technique that's very general. That's a thing that you can apply to a tube amplifier circuit, you can apply to an MOS circuit, a bipolar junction transistor circuit, a JFET circuit, who knows, in the future, a carbon nanotube transistor circuit, right? Whatever comes, this is probably the technique you're going to use small signal analysis, so it's probably the most important technique in this whole class. It's going to allow us to determine amplifier gains. It's going to allow us to determine frequency responses, which will be very important. That's how you shape what someone hears out of an amplifier or so. And then after learning a lot of the details then, we're then going to try to get you to analyze circuits by inspection. So that thing that I talked about, that big circuit that I claim you can analyze in 1 minute, by 140 you'll be able to do for that big circuit. But for some of the smaller circuits in this class, hopefully by the end of class you'll be able to analyze them in 1 minute too. You'll be able to just look at the circuit and inspect it and know what it's doing. And that's a very powerful thing to be able to do. It's all about understanding the complexities, but knowing what complexities you can ignore. And if you're able to do that, then suddenly you can analyze something a lot faster. And so we'll talk a lot about that during this class. It's using inspection analysis of different types of amplifiers here. And then finally, towards the end of the class, we'll start getting into digital circuits. So a lot of these things are analog amplifier circuits. Then we start getting into digital circuits. So things like CMOS inverters, ring oscillators. We won't go that deep into digital circuits because the place where you get that is really 151 and 251, those courses there. They'll go much deeper into that, but you should take this course first so you can understand the devices that are being used and understand at least some rudimentary sources that we can make for digital circuits. Okay, so that's pretty much the class. You see the final exam right here. You see one midterm right here. That's happening October 30th. Okay, someone has asked about exam conflicts with a lab. Can you make it up somehow? How would you have exam conflicts with a lab? Is that going to be... Actually, that's something we could talk about a little later. Is it okay to take 151 concurrently with this one? Yeah, I think you can. Because I think 151 will try to review at least some of the material that we have at the end of this course here. We'll probably go deeper. You'll get a better understanding of the physics and how these devices are working. I'm not sure 151 does that anymore. That's another course that's changed quite a bit over time as well. Someone asked about exam conflict. So the exams are kind of an interesting thing. This is a virtual semester, so I'm not sure exactly how we handle that. And what we might do, and they've told us that we cannot do things like Zoom proctoring. And so this may be something where we just open up the day and you can use your hour and a half, pick an hour and a half that you want to take the exam. So you'll sign on, you get the exam, in an hour and a half you have to turn it in before a portal closes. So we might do something like that, but we'll talk more about that later on. But you got 2 exams in this class, and I'm going a little too slow here, so let me speed it up a bit. So you know about your problem sets. Now the laboratory, you got a big thing about the laboratory. I kind of went through this already, but this sort of tells you, sort of gives you a nice summary of the lab. So here's lab 1 is sort of an introduction. These first labs are to get you to know your equipment better. And then these last few labs are actually design projects. So you can see the point totals for them are much stronger there. And what it really comes down to, you'll see all these labs when they come to you, but what it really comes down to, I discussed briefly the midterms and final, but it really comes down to this. This is the grading formula that I'll be using here for the class. So the problem sets are worth 15%. That's very small. And the reason why I do that is because I want to make sure that, if you want to, try to challenge yourself by doing them all by yourself if you can. So I know there's going to be people that may be working together on some of these things. On problem sets, I don't mind too much on that. But this is to encourage you to try to do your stuff by yourself, because if you can do that, that helps you a lot on your midterms and your finals. And so in this, you can see your laboratory projects, that's 35%. And so the projects make up a lot of that. Those are design problems, basically. And so the midterm and final make up about 50% of this class here. And the reason why I'm doing this, I used to have 2 midterms for this class, but I recently learned that, and a lot of other classes that I teach, I have 1 midterm. And so what I find is people like them both about the same amount. Having 1 midterm is a little more advantageous in this virtual world that we're in because of the stuff that we have to do, the hoops we have to jump through in order to ensure that there's no cheating going on and that sort of thing. Not that I think anyone's going to cheat, but I think if we can do things to prevent cheating, it at least gives people comfort that no one can cheat, right? I think, we're worried about cheating, so are you. I think at the same time. A lot of you are at the same time. So I think we owe it to you and to ourselves to try to do something about cheating in this case. If we can't do Zoom proctoring, then what we do are these exams, and the way I'm going to have to make these exams probably is the type of thing where they're going to be mostly design exams. So everyone is designing something different. It's going to suck to grade that, I guarantee you. But we have ways to do that. Actually, this is not an enormous class. It's got 40 people in the class, and that's sort of our max because we have to send out lab kits, and that's how many we have on that. But that's what the exams are going to be more like. They're going to be more like design problems, more like open-ended type problems, where everyone will have something slightly different. And that way we make it impossible to cheat. The other way to make it difficult to cheat is to make it just ridiculously hard, which might happen to. I'm sure a lot of you don't like that. But if that happens, you're all in the same boat. And what I found in the past, people like hard exams too. And it depends on who you are, right? You got to break it down by who you are. But that's the way we're going to try to handle this. We're going to talk about this a lot more later on in the course. But you'll see that we're going to try to do it in such a way that we're going to open up a 24-hour period. You're going to download the exam at a certain point, and a counter is going to start right there. An hour and a half later, or however long the exam is, you're going to have to turn it in to a portal that will close in that hour and a half. Okay, so that's what we'll do for the exam, at least for now. That's what we're thinking of doing. I think we will do that, actually. And so I've sort of gone through the syllabus. I guess, I could talk about grades a bit, and we're right at time here, but let me squeeze in this grade thing here. How am I grading? And we'll talk about this again, too, once we have some significant grades, like the exam grades and that sort of thing. But I'm using this Z sort of thing, so it's pretty much on a curve the way that we're doing this class. To calculate a Z score, what you do is you take your actual score, you subtract from that the average of the class, and then you divide that by the standard deviation. What this does is it turns whatever score you have into a number from 0 to, I guess, 2 is the maximum. That's not really the maximum, but I've never seen something much higher than a 2 there. But a 0, if you get a 0, that means you're right at the average. If you get a 1, that means you're a standard deviation above the average. And if you're above a 1, then you're more than a standard deviation above the average. And so, it really comes down to what grade is assigned for the average and a standard deviation above the average. Well, that changes from semester to semester depending on how people perform on the exams and different things, what they look like. So I'm not going to give a number for that right now, but I will say if you're a standard deviation over, generally you got an A. And if you're over standard deviation, you probably have an A+ or something like that. So that's sort of where it ends up being for the grading scale. We'll talk a lot more about this later on when we get to, say, after your first exam. But right here, this is how we'll do it. We'll do a Z for the homeworks, a Z for the midterm, a Z for the final, a Z for the labs, which include the projects, this formula there. And then we'll use this formula to get an overall Z, and then we'll take the Z of that too. And this formula here, these are those percentages that I showed you in that previous slide there. Okay? And so that's sort of how our grading will be done. Again, we'll be talking about this in more detail later on. I've been asking a lot of questions, or I've been looking at your questions through the chats, and hopefully I reached them all, or Kieran reached some of them while it's been happening, or Chotang as well. But does anyone have any residual questions right now?
About 113 that I didn't know. I haven't actually taken it, so.
Oh, there's a question about 113. Would I suggest taking 113 concurrently, or do you think it's best to take 113 first and 105 next semester? That's interesting. So I'm not sure what is the best thing to do. So in 113, I mean, that's kind of a newer brand of that course, right, with Robert teaching it. So I don't know if I dare say what's in it right now, because I'm not sure exactly what Robert's or Seth's, I know what's in it. And so I think that I don't know, I think you can get away with taking it. I think you'd be more comfortable taking 105 first, because you'll at least know more about the physics of the transistors. But you might ask,
That's my guess.
yeah, you might ask the instructor there also, what makes sense to do. For me, so 105 is meant to be the leader course into all the circuits courses. So it's meant to be the course you take first before you take any of the other circuits courses, and before you take the device physics courses like 130. And so I think concisely that's how I'll put it, but people have been daring enough to take some of these other courses concurrently at least. Yeah, I mean, if it can be done. I guess I will just say it can be done. People have done it in the past, 113 and 105 concurrently. Okay, question coming from someone who did not take 16B. Okay, that's interesting. That's pretty daring, but I think I just made you feel a little more comfortable with some of the things that I said about 16B. But I'm learning, what I know is that 16B is different in different semesters, and so if you took an older version, then you may know more, material than the newer versions, or it could be vice versa. Looks like I'm not, I don't know exactly what happened in the 16Bs. All I know from previously teaching this class is there's a lot of variance in that. And it's gonna, I'm gonna try to find out what you know, what you don't know, to make sure that we can fill in the gaps, if possible. Any other questions? I'm not sure that I answered that 113 question very well. I might not be capable of answering it well enough, so I think you should go to that course and ask the instructor. think the newer versions focus more on control theory. Yeah, that's what I've seen, that they're heading more toward the systems end, and so they're not actually giving you the background that you need to, that we'll need to get far in this course. And so how far we get in this course is also going to be dependent on what your background is as well. It'll be, we'll have to play it by ear here as well. Any other questions? All right, so it's 3:05. Thanks for coming, and I will see all of you on Friday. It'll be the same Zoom link, and you can also ask questions even offline if you want, send emails and that sort of thing. You've got Piazza as well. So thanks everyone for coming. Have a nice day, and I'll see you on Friday.